Okay, good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione. I'm a director of NITheCS. As you know, quantitative finance is one of the disciplines of NITheCS, so we are very happy to have again a talk in that discipline. Yeah? And it is my pleasure to introduce to you Professor Helgard Raubenheimer, the German version of the name. Yeah, we had this discussion this afternoon. Helgard is from the Northwest University, and he started his academic career there as a lecturer. And now I don't remember exactly the acronym. In what is it? In the Center for Business Mathematics and Informatics. And now he's the director of that center. Yeah? So Helga, thank you very much for coming to the long way to Stellenbosch, and we are really looking forward to your presentation. Thank you very much.
Thank you very much, Francesco. I appreciate kind words. Good afternoon, everyone. Thank you very much for listening to me. My talk this afternoon is on extremes in risk management. And it is a non-parametric approach to estimate the quantiles of compound distribution. So this is work that I've done over a few years with Rian de Jong, Tertius de Wet, and Charles Pretorius. These were one of those exercises or topics that started a few years back, and every time I got busy with administrative things, and every time I retook the project, it grew a bit. Finally, we are at a point where we've done a lot of work and we've submitted this for publication. So my layout of my talk this afternoon, I want to start off with just sketching the problem. Why do we want to estimate these extreme quantiles, and maybe highlight some of the issues that we have when we estimate these quantiles. I'll talk a bit about approximation methods. It will become clear why we need to approximate these quantiles. And then I'll introduce a new way of thinking of estimating these quantiles using a multiplier approach. So the first part I'll try to give a reason why we're doing this. And then we'll look at some numerical study and simulation studying, highlighting sort of the behavior of what we're trying to propose. And then I'm going to show you a practical example, hopefully showing you practically the application and the reason why we think this is a good approach. Okay, so our application is in risk management, and specifically we are looking at operational risk. But what I'm presenting here is also very much used in insurance as well, when modeling insurance claims. But our focus came from years of doing projects in operational risk in the banking industry. So the definition of operational risk is the risk of loss resulting from inadequate and failed internal processes, people and systems, or from external events. It includes legal risk, but it excludes strategic and reputational risk. Now, what makes modeling operational risk interesting is that unlike other risks, operational risk has no upside. So for in risk management, when you do market risk, I mean, you got risk because you want to make money in the stock market, right? So there's an up part, but you model the down part to protect yourself. The same thing with credit risk. Banks extend credit to people and organizations in the end to make money out of them. They pay interest rate and they make money, but they have to look at the risk if people default on the credit. Operational risk on the other side has no up risk. Just because you operate and you run your business, you've got operational risk, and you've got the risk of losing or receiving losses due to some of these things. And I'm going to start off with an example of just showing you some of the types of losses that you can get when you model operational risk, and try to motivate why we're looking at the extremes. So what I have here is some examples from the SAS Opera's global database. So this is a publicly available database that captures publicly available losses. In other words, it is a database of losses that was suffered, and this is publicly available data that companies report that they'd lose. So in the entire database, I'm just going to show you some of the largest losses to give you an idea of the type of losses that you can suffer. This database has over 60,000 losses recorded over 61 years, but I'm just going to look at the I'm going to exclude the non-financial losses. I'm only going to look at financial losses. So this is some of the examples, and what I plotted here was the loss values here is in the current value, so it's adjusted for inflation. And on that axis, I've got the log of 1 minus the empirical distribution function. So it sort of can show you these are your sort of tail events where the extremes are. And this is in millions. Okay, so you can see the largest loss in this data set was suffered by a subsidiary of companies, Marsh and McLennan. And when the loss was, so currently it's over 30 billion. But the loss when it realized was 21 billion. And I also show you at the bottom the categorization of the type of loss. So this is the Basel categorizations, business lines, and event types. So this is in clients, products, and business practices, asset management. And you can see the loss there is 21 billion, and this was due to people extracting their funds from the company when it got to light that there was fraud in this company. And people went in, and clients, corporate clients, you can see some of them, Walmart, and so on, took their money out of the company. And they actually, in the end, I think failed the company. And you can see the loss was quite big there. The second one I have here is a fraud case. So this is internal fraud in commercial banking. And you can see the loss there was 12.5 billion when it occurred. So now it's current loss, if you take inflation, is there, I think, maybe just below 25 billion. But in this case, there was a long run of fraud, internal fraud. They mentioned there Colombian cocaine cartels and Arab terrorists that took money through this institution. And the institution lost over 20 billion dollars. The one that I want to highlight here, just to show you the type of losses, remember that's why I'm showing you this. This is actually losses in JP Morgan that they reported due to the COVID pandemic, highlighting that they lost just over $10 billion due to COVID and the stress on the financial sector then. And this was specifically, if you read on credit losses of borrowers that suffered in that period. Then this one that I highlight here, this is the 2008 credit crisis. So Deutsche Bank got fined $7.2 billion for misleading practices during the credit crisis. And they had to pay a huge fine. And the last example that I have here is actually the 9/11 events. So this was the terror attack on the World Trade Center. This specific one is for an insurance company, was just below 300 million. The entire claim on the World Trade Center was 3.5 billion, but the property company that at that stage, I think it was months just before the event, they got a 99-year lease on the two buildings. They actually were allowed to put in two claims because it was two events. One event was 3.55 billion, and they actually made a case that because it was two events, they can have a second claim of 3.55 billion. I think they got around over 4 billion or something like that in the end. But I mean, that was a large loss for the insurance industry. So this is the type of losses that we're trying to model when we model operational risk. So you can see why we talk about extremes, because these are in the tails of this. Okay, so how do we model operational risk? And what we're trying to do is we want to model the capital that a financial institution needs to keep. So regulatory capital or economic capital. And how we model this is using compound distribution. So it is the random sums of losses. So what we do is we model the size of the loss using some severity distributions, and these are typically loss distributions, so they skew to the right and they're very heavy-tailed. And then the frequency, that is the number of losses over a certain horizon, and for modeling purposes we use an annual horizon, so we look at the annual aggregate losses. For that, we can use something like the Poisson distribution. You can use something else like negative binomial or binomial. All the results can be generalized, but it's very common practice to use something like a Poisson distribution. And then what we're interested in is this compound distribution, which is the random sum. So it's a sum of these losses, but the amount is also a random variable. And this is called a compound Poisson distribution. And we are interested in estimating a very high quantile of this. So regulatory purposes, financial institutions need to calculate their capital at a 99.9% on this annual aggregate loss distribution. This is sort of like a 1 in 1,000 year event that they want to keep capital. Economic capital is typically set at very, very higher values. And this is what we're trying to do. Now, this can be very difficult because, as you see, we've got very little observations in the tail, and they're quite large observations. The other thing is when we want to calculate this quantile is that you cannot calculate this analytically. You have to do that numerically. So you have to use some approximation technique. So very easy is using Monte Carlo simulation, brute force. In other words, you can simulate 1 million observations from this. So for each simulation, you'll simulate a random number from the frequency distribution, and you will simulate that number of observations from the severity distribution. You will add it, and you repeat that process lots of times, like 1 million times, and then you've got empirical distribution, and you can calculate your quantile. There are other methods like the Pange recursion and the fast Fourier transforms. Now, what we're interested is in more to look at closed form approximation, since that's not where you approximate the entire distribution, but you try to approximate just the quantile. And there are actually methods that you can do that. So the first one is the single loss approximation, and the other one is perturbative approximations. And I'll talk a bit about them now. But I want to digress just a bit and show you why is this, what's the problem here when we approximate or estimate that quantile. So I'm going to include a few things from extreme value theory, which is the study of extremes in statistical distributions. But the other thing that I'm going to mention quite a lot is the extreme value index, which is a parameter that controls the behavior of the right tail of these distributions. Now, just to indicate to you the effect of the extreme value index and frequency when we model the quantile of this distribution. So I've got here an example. I'm using a bird distribution. It's a bird type 12 distribution. It's got 3 parameters. It's a scale parameter, and then location, and then scale and tail parameters. So shape and it's the location parameter and the shape parameters. Now, this is the distribution function. The extreme value index for this distribution is, you can calculate it from the parameters, 1 over the tau and the alpha. Now, the extreme value index indicates to you the, as I've said in the previous slide, the heaviness of the tail. So it's the parameter that governs the tail. So if it's below 1, then you can actually, it's less heavy-tailed. And above 1 is very heavy-tailed. And at a parameter of 1, usually you can't calculate the expected value of the distribution. So above one, we've got um, undefined means. Below a half, you can calculate the variance. Below a third, you can calculate the skewness. Below a quarter, you can calculate the kurtosis, and so on. But what I'm showing you on the graph here is, first of all, what we did was to, in this case, just approximate the 99.9% quantile of the distribution for the different parameters. We repeated the process 1,000 times. So we did 1 million simulations to estimate the quantile, and then we repeated that process 1,000 times. And what I'm showing you is the confidence interval of that. So 0 was the median, and we're just showing you actually that thing that you're approximating, what's the variance around that. And so you can see the higher the extreme value index, the larger that that confidence level around what you're trying to approximate. And the lambda, the frequency, the higher that, obviously the smaller that. Okay, so this is just to highlight the uncertainty in what we are actually trying to approximate if we actually know what the distribution is, right? In general, we don't know the distribution. We just have some data, and we have to go and calculate this. Next is just, again, trying to highlight a little example of what these large values in the tail of the distribution can actually have on what you're trying to estimate. So what I have here is, I'm assuming that, let's say I know that my losses comes from this bird distribution, and my extreme value index is 0.83. I'm going to assume I've got a lambda of 10. In other words, I'm going to get 10 losses a year. And let's say I've got 10 years worth of data, so I should have around 100 losses. So the left-hand side there is, that's the truth. So that's just the distribution function. That's just on a log scale so that I can see the tail there. And what I'm showing here, again, is using Monte Carlo simulation of 1 million replications, and I'm repeating the process 1,000 times. And that is the spread of the quantile, the 99.9% quantile. So I know the true value should lie somewhere there. What I'm doing here is to say, okay, well, let's say I only have 100 losses. Let's say I have 100 data points from this distribution. Now I go and fit, again, a bird distribution to the data. I get this bird distribution. That's my parameters. That's the extreme value index. And again, from this, I'm doing the 1 million simulations, repeating it 1,000 times, and that's what I'm then calculating. That's the spread of my error. So you can see from the data how that actually compares to the truth. On this side, all that I did was just move 1 point very far in the tail. So typically what you get in these situations when you model operation is sometimes 2 losses gets counted as 1 loss. And then you got a large extreme value. So you can see how one value very far in the tail, doing the same process, again fitting a bird distribution, that's my extreme value index, and that's the approximation of the quantile. And you can see the large difference in the different values. So what do you keep for capital then in the end? Okay, so that's why I just highlighted a lot of the issues. So in general, in practice, you do get things like using external data because you don't have enough on your own data. You use scenarios and things like that, which improves it, but I'm not gonna look at that now. Okay, so and now I'm skipping to the end of my presentation where I'm gonna show you the practical example, but I'm gonna leave a part out. I'm gonna leave the part that I did out here, the multiplier approach, and I'm gonna go and get back to this in the end again. So what I did here again was look at the SAS Operas Global Database. In this case, I'm not looking at all the data. I'm just looking at a specific unit of measure or a operational risk class. So I've got a specific event type and a business line. For this, I've got 323 observations. Over 61 years, I've got a frequency of 5.3. So what I did was the following. I fitted different distributions to the data set using SAS proc severity. Works quite nice. It can fit different loss distributions to your data. For example, a Burr, inverse Gaussian, log normal, Weibull, and so on. And specifically, I'm also looking at mixture distributions where I've got a log normal in the body and I've got a generalized Pareto in the tail of the data. Okay. And then what I'm doing is I'm going to look at the best fitting distributions, and then I'm going to use Monte Carlo to approximate that 99.9% value at risk. And this is what I get. So what you can see here, the best fitting distributions here was the Burr, the log normal, and the log normal with the GPD tail, which was fitted from the 90th quantile. So what you can see here, if I just look at log likelihood, the log normal with the GPD tail fits the best. If I look at some other fit statistics or measures, then the log normal becomes better because it has less parameters, so something like your archaic information criteria and the correction and the Bayesian, Schwarz Bayesian criteria, they would prefer the log normal because it has less parameters. But if you look at something like KS and Annis and Darling, the log normal also fits better, but if you look at Kramer von Misses, it fits better, the Burr distribution. If you look at the quantile plots, they look very similar, so you can't say that the one fits probably better than the other one if you just look at quantile plots. But if you look at the actual value at risk between them, you get quite different values. In this case, it's 8 billion for the Burr, or 8.5. It's just over 5 billion for the log normal, and the one with the GP details around 6 billion. And these are the extreme values. So log normal has extreme value index of 0. So the question is, which of the capital should you then keep? Right? So if you ask the business manager, then he will say keep the lowest value. And if you ask the regulator, he will tell you to keep the highest value. So the question is, which is obviously better? But what I want to mention here is, obviously the log normal does not, you can see here, there is heaviness in the tail, which the log normal doesn't fit there. But okay, I'm going to get back to this in the end. Okay. So now what I want to do is to introduce you to the approximation methods, because our multiplier method, which in the end does not use any of the fitted distributions but works non-parametrically, is based on these approximation methods. So these approximation methods are closed form. So in other words, you don't have to do any simulation. If you have some, if you know or estimate the underlying distribution for the severity distribution using some distribution, and you've got your frequency parameter, you can actually just plug it into a formula and you can calculate the quantile of the compound distribution or approximate it. And they're very easy. So both of them, the single loss approximation, which was proposed by Becker and Kluppelberg, and the perturbative approximation that was proposed by Hernandez, they both estimate or approximate. Sorry, I'm using approximate and estimate sort of interchangeably, but they do have, in our sense, different meanings. Approximate is if you know the underlying truth, then you can approximate the quantile. And if you don't, if you just have data, then you can estimate that from the data. But both of these, you approximate the quantile of the compound distribution using a quantile very far in the tail of the frequency distribution. So here you can see the quantile can be approximated by the quantile of the severity distribution, which is then estimated at the point of gamma. That's the quantile of the compound distribution we're trying to estimate. In this case, gamma would be 0.001, and lambda is the frequency parameter. So you can see the larger the frequency, the farther into the tail of this compound this frequency distribution you are going to estimate your compound distribution quantile. But I've highlighted to you in my previous examples how very difficult this becomes because you don't have a lot of data there, and it is very much driven by the largest loss in your data set, which can be a problem. Okay, and similarly with the perturbative approximation. Just to highlight in our examples, this is now the larger example, all the data. You will be looking at that quantile of the severity distribution, and in our practical example that I'm going to show in the end, you'll be looking at that 99.9811 quantile of the severity distribution. So you pretty much, the capital is driven by the largest loss in your data set. Okay. So just make quickly some corrections on these. So Deegan in 2010 proposed second order or using second order exponentiality. He derived improved single loss approximations. So what you can see here, if you've got a finite loss distribution, a finite mean, in other words, your extreme value index is below 1, you add lambda times the mean. And if it's an infinite mean model, meaning your extreme value index is above 1, you multiply by this correction term, and this helps to improve the values. The perturbative approximations follows the following formula. You've got the sum for the kth order. So a zero order, you just approximate using this quantile of the severity distribution. First order, you add this term with the expected value. Second order, you look at the squared expected value. But you've also got these terms, which is the density of the severity distribution in the point of your first approximation. Okay. And in another study, we've showed that in practical cases, the perturbative approximation, second order, works quite well for different range of distributions. Okay, but what we're trying to get to is the following, is to say, well, is there a way, rather, because we know little of this tail, right? Is there a way that we can rather do the following? Can we use a multiplier approach? In other words, can we approximate this quantile using some multiplier, but a less extreme quantile? Okay, so in other words, we want to use a less extreme quantile at this point, and we want to multiply that by the multiplier to get this quantile of the compound distribution. And the answer is yes, we can. Using extreme value theory, we can show that if we approach this from the single loss approximation, this would be the form of our multiplier. So again, the multiplier has the following things in it. It has the frequency. It has the quantile of the compound distribution we're trying to approximate. It includes the extreme value index, the kappa, and also the p star. That would then be the quantile from where we are multiplying from. Okay. And in the perturbative approximation, it has a I want to say similar form, but again, it's got those values in it. And the other question then is, can we do this empirically? Right? So in this case, if you know the true underlying distribution for the severities, then obviously you can go and calculate the kappa, and if you know the frequency, the lambda. But the question is, can I do this empirically where I don't assume any parametric form of this underlying distribution? And I'll show you that in the end. Okay, so I'm going to quickly run through some of the mathematics, not to waste time, but we can prove these multipliers using extreme value theory. Prof. Tertius will tell you that this is very beautiful mathematics, which it is, but it's very useful. The first thing that helps with calculating these multipliers is using sub-exponentiality, and that is the different types of distributions that we're using are part of the sub-exponential class, and they all have regular varying densities. So a regular varying function is a function where if you look at the limit as t goes to infinity of the function at the point tx over the function in point t, as t goes to infinity, this goes to follows a power law. In other words, if you go down this function and t goes to infinity, there's always some slope in that function at the tail. It doesn't go flat, right? Because it goes flat, you've got a slow varying function. And this is the type of distributions we're using. In other words, it's heavy tail distribution. The other thing is using a theorem. If the density, the Karamata's theorem, if the density is regular varying, then it is its survival function is regular varying, as well as quantile function is regular varying. And then lastly is if we look at slow varying function, so there you can see in that case the limit, if t goes to infinity, it goes to 1. So in other words, if we go very far, then that sort of becomes flat. Is then that we can write regular varying functions as this term times a slow varying function. Now, putting all this together, and I'm not going to go through this line by line, but putting this together, we can actually show that you can, which has been shown quite a lot, that you can approximate the quantile of the distribution using a multiplier and a lesser quantile. Right? This is a well-known in literature as well. But if we put this together with the single loss approximations and the perturbative approximations, we can get our multipliers. So in other words, we can approximate this quantile using a quantile not that far in the distribution using the multiplier. And then we can apply this further. We can extend this to second order extreme value theory. In this case, we not just have this multiplier, but we've got this second term here. And what we have here, and I'm not going to go into the mathematics, is but we got a second parameter, which is the second order EVT or EVI parameter, which is the row. So we don't just have the EVI, but we've got the second order row. And that can give us a second order extreme value index multiplier, which corrects better. Right. So in the end, we've got the following. If we approach this multiplier from the single loss approximation, then we have the following. We can use approximate this quantile, and our multipliers becomes the following. For the single loss approximation with a first order EVT, this is our multiplier, and for the second order EVT, this is our multiplier. And then the quantile estimation looks something like this. So it is the multiplier, first or second order, times the lesser extreme quantile, and we can also add the corrections from Deegan. Okay. And similar with the perturbative approximations, this is our multipliers, and we can add the corrections. So the first order correction, we can add that. And the second order correction, here you can see it's a bit different if you go look at the start of my slides, but we've also used EVT to get better approximations for these because that's sort of the derivative of the density, and we can get some extreme value approximators for that as well. Okay, so what do we have? We've got the following in the end. We've got a different set of multipliers. So we've got multipliers from the single loss approximation approach, and we've got multipliers from the perturbative. We've got first order EVT multipliers, and we've got second order EVT multipliers. So the first thing that I'm going to show you now, and I'm going to start moving faster, is to what we did was just to do a numerical study. So what we did was to assume that we know the underlying distribution, and we looked at a Burr and a Frechet type distribution, but I'm just showing you the Burr one in my slides. And what we did again was the following. We assumed that we know for different parameters the underlying Burr distribution, and for the different types of multipliers, we calculated the quantiles. But we're measuring it against obviously, we don't know the actual quantile because we have to approximate it. So what we did to get an estimate for the quantile was, as I've showed you in that other slide, we selected or generated 1 million observations from the compound distribution. We then calculate the quantile from those 1 million observations. And then we repeat this process. For this examples, we did it 10,000 times. And then we take the median of those as our estimate for the quantile, or approximate for the quantile. Okay, and this is what we get. So this is, for example, a Burr distribution. I've dropped the eta parameter because we use it as 1 throughout. it has an extreme value index of 0.5, and it's got a second order EVT parameter of minus 1.5. What I have here at the bottom is the quantile from which we multiply. So the P star is where we multiply from. So we're multiplying from 90%, 925, 95, and so on. And at the top here is the quantile we are multiplying to. That's the compound distributions quantile we're approximating. This is the case where we're mostly interested in, right? So this is where we calculate capital. But for interest sake, we've included some of the other ones, the lesser quantiles. And the dotted line is first order EVT, and the straight line is second order EVT. And I've got single loss approximation, first order PA, second order perturbative. So here we can see that obviously the case where we're looking for, in other words, where we estimating very far in the tail, we can see these the multipliers behave well. And we can see obviously that the second order EVT approximators are in general better. Right, so if we're not that far in the tail, they all don't seem to behave that well, which is expected. This is now where I've got a EVI of 0.5 and I've got a rho of -1. So what we can see here, if we're multiplying from not that far in the tail, first order approximators are struggling, where the second order approximators are again performing okay. But this is the interesting case, and this is where the rho is -0.5. And this is, in general, in extreme value theory, this is the not so nice behaved distributions. So what we can see is that they are struggling if our second order EVI parameter is 0.5. Again here, perturbative approximation seems better, the second order ones. And if we're multiplying not that, so if the multiplication area is not very large, then it's better, but that's also expected. Okay. And this is another example where the extreme value index is 1. So here again, we can see the behavior is not that bad, but if we get to the case where we've got the -0.5, then they struggle. But this is, if you read EVT literature, this is somewhat expected. Okay, so what we have here is we see the second order EVT multipliers perform quite well, in most cases, okay. We've got the problem where the rho is closer to 0, but we see also that for where the quantile we are interested, the 99.9, the perturbative, and the others do perform not that bad. Okay, so, but what I said at the start is that what we're trying to do is to look at non-parametric estimation. So what we can do in these multipliers is that if we've got a data set of n observations over a years, we can obviously estimate the frequency using n over a. And then we can also fix this p star, which remember is the quantile we're multiplying from. So what we want to do is to fix that. We want to calculate k star as follow. And then what we're going to do is this lower quantile, we are going to estimate that using the order statistic. Okay, so we're using a we're not fitting any distribution and assuming some distribution there. We're just using the order statistic to as our quantile that we multiply from. We can, with P star fixed, we can calculate this K star, we can estimate the frequency, and then we can use general extreme value theory literature. We can estimate the extreme value index using the bias corrected yield estimator, and we can also estimate the rho. And this also has a beta in it, but we can estimate this from the data. Okay, and we can update our our multipliers using these estimates. Right, so what we did here before I get to, I'm almost through it. is in what we first did was just to look at the behavior of the non-parametric estimations using a simulation study. So what we did was to assume some parameter and some A for the number of years, and then we have N, which is lambda times A, and we draw that number of observations from our data set. To say we've got 10 years, a frequency of 100, so we draw 1,000 observations from this data set. And then what we do is we calculate all these estimators for lambda, for the extreme value parameters, the EVI, the rho, the beta, and we check how they perform. Again, to check it against is we do this 1 million simulations, replications from Monte Carlo simulation. We repeat that 10,000 times and we take that median as the true value. Okay, and this is what we got. So this is for, I think the kappa here is again a half. What I'm showing you here is the multipliers, first order and second order multipliers for single loss approximation, perturbative, and perturbative 2. And again, here at the bottom is the P star. In other words, a quantile we are multiplying from. And in all cases, we're estimating the 99.9% quantile. Okay, so again, we see that the second order behaves better. In this case, what we see is that for the second order, doesn't matter where we multiply from, but it sort of looks more stable. And this is just to show you the variance. If we look at some of the other, this is where we multiply from, and this is to look at the effect of the sample size. So obviously, as you expect, the larger your sample size, the better you can approximate using these methods. Okay, but in general, again, if the rho moves to -1, we've got this deterioration specifically for lower samples. I haven't shown the one for -half, but we know that's a difficult case. Okay, so what we saw from the simulation is that both finite and infinite mean, the PA2 and the PA1 and the SLA are comparable, but again, we prefer the second order multipliers to the first order multipliers. Okay, so now let's get back to the practical example to see actually how does this fit into what we normally do with a parametric approach. So again, on this data set that I've showed you at the start, I showed you the different distributions that we fitted and that they all seem to fit quite well from what we can see. It's very difficult to choose from the two, but what I'm going to do now is to compare the Monte Carlo simulation with just PA2 in a parametric sense, and then also look at our non-parametric multiplier on a PA2 with the second order EVT. Okay, these results you saw earlier. So here at the bottom, just to highlight, the estimate for the extreme value index is 0.81, which is close to the Burr and in the same range as the log normal, indicating that a log normal with the GPD tail, indicating that a log normal might not get the tail of the distribution quite well. The rho was minus 0.65, so it is closer to 0, so it is maybe a difficult case. But this is now the quantile approximated if we multiply from 90% or if we multiply from 95%. So this is the quantile, let's see, 7.6 billion and 8 billion, which is actually in the range of the log normal and the Burr that we previously had. And what I want to show you here is actually if you range the K star from 1 to high, so this is the number of exceedances. So here I've just indicated if the K star is here at 16, you get, we multiply from 95 quantile, and if the K star here is at 32, we multiply from the 0.1. But what's interesting here is that we get this region that seems to be stable when we look at the capital, the quantile estimation, and it is also in the range of those two of the Burr and the log normal. Okay, and in this case, we had no assumption on the underlying distribution. And what's more interesting, and I'm going to end off with this, is what we did was to look at the variation of these estimates as well. So what we did was to resample from the data set with replacement. Again, so we resampled 323 observations. We repeated this 1,000 times, right? Each time, um, in this case, we did not do the Monte Carlo simulation. We just used the PA2 estimate to estimate the, so we refitted the Burr, the log normal, and the log normal with the GP detail on this resamples, on this 1,000 samples. So we refitted the distribution, and we used PA2 to estimate the quantile. So we did not redo the Monte Carlo simulation. But we also did the same using the nonparametric multiplier, multiplying from 95 and 90% quantiles. And then we've plotted the variation using box plots, and I'm using a log scale just to fit everything into one nice graph. So here you can see the variation for the Burr and the log normal with the GP detail, the log normal not fitting the tail, most likely quite the tail behavior, very smaller. But this is the variation for our multipliers, which is comparable, if not maybe better, than the parametric ones. And we get estimates for the quantile, which is in the same range. Okay, and this is what I wanted to show you. We're using a non-parametric method and using some nice mathematics and extreme value theory to get something that's practical in our sense if you model operational risk. Okay, thank you very much.
Helga, thank you very much for the very informative talk. We'll try to apply to the NITheCS operational risks. Are there questions from the professional audience here to Helga? Please.
Yes, thanks, Helgard. I thought this was a very nice, nice talk to learn from extreme value theory. I have one quick question regarding this extreme value index. You consider the Burr distribution, and then you give us that nice formula 1/tau times lambda. And if you go to the mixture of a normal, a log normal with G or PD, general Pareto distribution, is there a way you can actually compute that EVI, that extreme value?
So in that case, where we've got the log normal body with the GP generalized Pareto distribution in the tail, that would be the extreme value index of the generalized Pareto distribution.
So you can also get it in a closed form.
Yeah, for the generalized Pareto distribution.
Oh, okay. And so the index, what does it tell us?
So the index tells you, it tells you about the heaviness of that tail. So if it's higher, then the tail is heavier. In other words, you've got more weight in the tail of that distribution. So it dies down very slow. It goes on and on. So the thing is, you can get quite large, extreme observations from that tail, which is the type of data that we observe. In other words, we've got these low frequency, high severity. So it doesn't happen often, but if it happens, it's quite severe. Where a normal distribution dies down slow. These distributions, the tails carry on quite long.
Okay, so my question is, in the simulation, do you also consider very unusually large observation that may not belong to, let's say, the underlying distribution?
Sorry, just repeat the question.
I'm asking, in your simulation, do you check the presence of, let's say, an unusually large observation that do not belong to the distribution you are considering?
No, we're not doing something like that. Yeah. Yeah, to actually see if
and any other questions? Here we go. So,
Thank you for the talk. You know, in operation risk, you gave a very nice example when you started. COVID being one of them, and I think some losses that companies have experienced. What's in my mind is because some of these losses, they happen once and they are done. Is there maybe a way on which this can be suggested to the maybe Basel or the regulators so that maybe they have some capital they set aside for operational risks? And do you think it will be too much if they use this type of model?
Do you mean so something happened? So maybe there's something in place to cover that it doesn't happen again. Now
Yeah.
you're keeping too much capital.
Yeah.
So
I think another thing is maybe to keep it simple, is there a regulation already for capital to be set aside for
So
operational risk?
So this is the typical way that you model that capital that you set away for operational risk. So you have to look at these losses and you have to go through this process. But this is very simplified. So there's a lot of things that you can build into this, looking at using external data. In other words, not just your own data from, for example, maybe using this database that I'm showing you here, but then there's things that comes into play like scaling the losses because your operation might not be big. So you cannot suffer 3 billion loss, but you can suffer a similar loss, but maybe smaller. So there's scaling of those losses, incorporating that. There's incorporating scenario from experts, things like that. Then again, there's also things like it should be forward-looking. So you can say, well, okay, I've suffered these losses in the past. I've put in things in place to not, so I'm not expecting maybe larger losses. Or it could be that you can see, fraud is on the uptake. So it might be that you need to increase something. Or things like that that can be included in this whole process. So it becomes interesting thing.
Just one more question from me. Just a clarification. You said that the frequency and the severity distribution, you simulate them. So I just wanted an explanation there, how you put them together.
Yeah, so if you simulate the compound distribution, and that's this first slide. So when you simulate the compound distribution, right? So it's the random sums of losses. So you first simulate an observation from your frequency distribution. So for example, if your Poisson distribution had a frequency of 10, then if you simulate from that, you'll get a value like 9 or 8 or 7 or 11 or 12. And then you simulate that number of observations from the severity distribution, you add them. Now that's one simulation. Then you repeat that process 1,000,000 times. And then you've got 1,000,000 observations and you can estimate the quantile. So what we did to get a better estimate of that is to repeat that process 10,000 times and take the median of that as sort of the true underlying value. That's why, I mean, if you take this, if your frequency is quite large, 1,000, right? Then you can see, even though we've got nice computing power these days, if you have to do this, it can be quite a large simulation. And if you've got, they do this in smaller things like that they call operational risk classes or units of measure, and then they aggregate this to a larger part, then including dependent structures and things like that. But then it can take a while. That's why using things like approximation methods where you can fast gauge the value is important before you go into the whole simulation part.
Any further questions, or do we have questions from our online participants? No, no question. Then Helgard, as a little sign of our gratitude for your talk, this is a magazine that NITheCS co-publishes. Yeah, so thank you very much for your talk.
Thank you very much.
Thank you
I
very much.
appreciate it.